Hi, this is Shyamala Gauri, Assistant Professor in CSE Department, Rohini College of Engineering and Technology. Subject code CZS 355, Neural Networks and Deep Learning. Unit 3, Third Generation Neural Network. The topics covered in this presentation are applications of CNN, in which computer vision, image generation, and image compression are explained. CNN application. Number one, computer vision using CNNs. Computer vision refers to the field of artificial intelligence that enables machines to interpret, understand, and make decisions based on visual information from the world, such as images or videos. CNNs have become the standard method for solving many computer vision problems because they are particularly well suited to recognize patterns, detect objects, and extract features from images. How CNNs are used in computer vision. Feature extraction. CNNs automatically learn hierarchical features from the raw pixel data of an image. In early layers, the network detects simple features like edges and textures, while deeper layers capture more complex patterns like shapes and objects. Image classification. CNNs are widely used for image classification tasks where the goal is to label an image into one or more predefined categories. The network processes the image through multiple convolutional layers and pooling layers to reduce the dimensionality and obtain a compact representation of the features, followed by fully connected layers to make the final prediction. Object detection. CNNs can also be used for object detection, where the goal is to locate and classify objects within an image. Techniques like YOLO, you only look once, and faster RCNN extend CNNs by using additional layers for bounding, box prediction, and object classification simultaneously. Semantic segmentation. In segmentation tasks, CNNs are used to classify each pixel in the image into a category. Fully convolutional networks are commonly used for this purpose, where the convolutional layers are adapted to output pixel-wise predictions. Number two, image generation using CNNs. Image generation involves creating new realistic images from certain inputs, often for tasks like generating art, photos, or realistic images from sketches or text descriptions. How CNNs are used in image generation. Generative adversarial networks. GANs consist of two neural networks, a generator and a discriminator. A generator's goal is to produce realistic images, while the discriminator's goal is to distinguish between real and generated images. Capturing spatial hierarchies. Convolutions help networks learn spatial hierarchies, starting from low level features like edges and progressing to more complex patterns like textures and objects. Parameter sharing. Instead of learning a different set of parameters for each part of the image, a convolutional filter is applied to all regions of the image. This significantly reduces the number of parameters, making the model more efficient. Translation invariance. Since the same filter is applied at different positions in the image, the network can recognize features regardless of where they appear in the input. This makes CNNs robust to translation changes in images. CNNs are used in the generator to generate images and in the discriminator to classify real versus generated images. The CNNs help the generator learn how to create more realistic images by learning from the feedback provided by the discriminator. GANs, especially variants like DZ-GAN, Deep Convolutional GAN, leverage CNNs in both the generator and the discriminator to produce high quality realistic images. Autoencoders for image generation. Variational autoencoders are another example of CNNs being used for image generation. VAEs learn a compressed, low dimensional representation of input images and then generate new images by sampling from this latent space. The encoder part of VAE typically uses CNN layers to extract features from the input image, while the decoder uses CNN layers to generate new images from the latent representation. Number 3. Image compression using CNNs. Image compression refers to the process of reducing the size of an image file while preserving its quality as much as possible. Traditional methods like JPEG and PNG rely on algorithms such as discrete cosine transforms or Huffman coding to compress the data. However, CNNs have been shown to perform better in some cases, especially in terms of visual quality and adaptability. How CNNs are used in image compression. Compression and decompression with CNNs. Autoencoders. A CNN-based autoencoder architecture can be used for image compression. The encoder network learns to map an image into a compact, low-dimensional latent space, while the decoder network reconstructs the image from the compressed latent representation. End-to-end compression networks. Learned image compression. Researchers have developed end-to-end systems where a deep convolutional model learns both the encoding and decoding functions, often using techniques like rate distortion optimization to balance between compression rate and distortion. For example, deep image preer is a method that uses CNNs for image denoising, super resolution, and compression, all learned from the input data. The network is trained end-to-end to minimize the reconstruction loss, which ensures the decompressed image looks as close to the original as possible. In the context of image compression, the encoder will compress the image by progressively reducing its spatial dimensions through convolutions, while the decoder will use deconvolution layers to upsample and reconstruct the image. Lossy and lossless compression. Lossy compression. CNN-based methods often result in lossy compression, meaning some information is discarded in order to reduce the file size. However, with the right training, the visual quality of the image can be preserved, and the compressed image can be much smaller than traditional methods like JPEG. Lossless compression. While CNNs can also be used for lossless compression, where no data is lost during compression and decompression, achieving effective lossless compression with CNNs is still an active area of research. The goal is to achieve compression without sacrificing image quality. Thank you.